Alrighty, guys. So the purpose of this video is I just want to show you what you're going to be doing and then walk through just the math portion. So you are going to go through these guided notes, okay? This is an example that I want you to work through. And then you're going to do this assignment right here. This part below is just kind of I called it a cheat sheet, a little step-by-step guide. This math is not hard at all, but I'm making this in case someone's not here, and there's I want to go through one example with you. So if we go to the water supply presentation, I'm not going through the whole presentation. I'm fast forwarding all the way to this example, and that's what I want to walk through with you. So you're given all this information about a water supply system. Again, I'm assuming you've already gone through the notes. This is not going to make a whole lot of sense unless you go through the first part of the guided notes to get some of that background knowledge. Please do that first. So we have our elevation difference, our type of our pipe, the gallons per minute, how long it is, all the different fittings, and then the goal of all of this is to find the pressure at your faucet. So that's what we're going to go through. So we know that it's 3.2 miles. We're going to convert that to feet, 5,280 feet in a mile, of course. So here's our total feet. Great, easy. Now what we need to do, the last slide gave us all this information about all these different fittings. And take note, it's a 10-inch flanged cast iron pipe. And let's find this first one, 7 regular 90 elbows. Okay, so let's open this up. And let me actually back up for a second because it says flanged pipe. So these are screwed fittings. You see this in much smaller diameter pipe. We see flanged fittings with these really big bolts and nuts that hold pieces together. This might be a 2-foot or 3-foot diameter pipe, a really large pipe. If you've seen the big pipe in Ogden Canyon, that delivers our drinking water from Pine View, and that's a huge pipe. So flanged fittings. Okay, so back to my table. And so notice flanged fittings here, screwed fittings here. It was a 10-inch, and right here, I know that's a little small. There we go. So here's our diameter, 10-inch, regular 90, just like a 90-degree bend, and that is going to add 14 feet. That's going to add 14 feet to our pipe. And so if we go back here, there are 7 of them. So we do 7 times 14, and you're going to do that with all of these different fittings. So then what you do is you take, remember that's 16,896, you're going to end up with 462.8 feet, and add that. We have to add that to our total length, because all those fittings end up creating basically feet of pipe. We're going to make turns, we're going to make 90s. It's going to reduce the pressure and the force, so we have to take all of that into account. So this equation looks ugly. It really is not. So it's our Hazen-Williams formula, and let's just jump in. So 10.44 times our total length after we accounted for our fittings, that's this 17,000. Q was given, that's our 110 gallons per minute raised to 1.85, easy. The denominator is what type of pipe we have. I'll show you that chart in just a second, and the diameter of pipe, and these two exponents are just constants in our equation. And let me show you. So it said cast iron pipe. Let's talk about that. Here we go, cast iron pipe. Unless the problem specifically says clean new pipe, then we would use this. If it does not say it, and our problem, our scenario did not say clean new pipe, then we're just going to use 100. And that's this typical design value. Okay, so let's see where we were. Yeah, see, cast iron pipe doesn't say anything about it being new. Okay, we did our Hayes and Williams, we did some ugly math, and we got down to 2.94. There are some quiz questions on this. Make sure you know how to do it. And then back in your guided notes, I put, yeah, right here. If you put your parentheses in exactly like this shows, you can get it right on the first go in your calculator and not have to do the numerator separately from the denominator and then divide them. Okay, getting sidetracked. Here we go. All right, we got 2.94. We're almost done. That's the hardest part. So also in the problem, it gave us our like the height of our water tower, and then the elevation of our water tower, and the elevation of where this house or where whatever is. So we take the difference and we get 241 feet. We need to convert that to pressure. Right now this is what we call static head. We need to convert that to pressure. So we convert that and we get 144 psi. 2.31 feet is equal to 1 psi. So we take that 241, this slide's a little confusing. We take that 241, yeah, you can really omit this step actually. Let me back up. Take the elevation difference, then subtract what you got from Hayes and Williams. There's that 2.9, you get 2.38 feet, and then convert that to pressure. These are just showing two different, don't worry about this step. This step's dumb. So elevation difference, subtract Hayes and Williams, convert to pressure, you're done. So I just wanted to walk through one with you. It seems a little crazy at first. It's really, really easy. So again, you should have already done your notes. Do this example. I'll put the link to this video up here somewhere. Here's your actual assignment. And then here's just a cheat sheet of basically what I just said. And then also here are some of your, all of your charts that you'll need, some links that you'll need. I tried to put all of that just on one document.